as Daniel introduced, I'm a computer scientist, and I work on computer vision, or in general, like visual computing and machine learning. And I will start my talk with some really exciting progresses happened in my research area. So for example, nowadays with machine learning, with computer vision, the computer graphics, we can reconstruct, does it work? Yes, such nice geometry, right, of a landmark from a collection of online photos instead of a 3D scanner. And also we see embodied agent inside such like a realistic environment, right? So now people can train embodied agent in realistic environment to do exciting, challenging computer vision tasks, for example, scene understanding, navigation, and many others. But if you take a closer look at this result, or this environment, a limitation of such environment is it doesn't contain people. Right. But if you think about if we want to train an agent to work and live together with humans, they really need to see people as well, right? And then the next question you might have is why there's no people, realistic people in such simulation environment? So this is just a few examples like I find online, but if you take a look at them, like we humans, right, we have articulation, like we are highly articulated, we have different motion, different poses, and also we have different body shapes, we have different clothing, and also we interact with each other, social interactions, we also manipulate objects. So it's actually a very, very challenging task to understand human or to reconstruct and understand human poses, to predict human behaviors from images from videos, right? And it's also a very challenging task to synthesize or generate realistic virtual humans and bring those realistic virtual humans into the virtual environment. So that's basically the focus of my research. So we focus on understanding and modeling 3D humans for real-world applications. And this is also the kind of like the outline of this work. So the first part is perceiving and reconstructing real humans. So I will present a project where we try to reconstruct human motions from monocular RGBD videos. And the second part of the talk is about synthesizing virtual humans, where I will present several works where we try to synthesize realistic virtual humans in 3D environment. So let's start with the first one. So when we think about human motion capture, right, what's the best human motion capture system we could get? It's really in the film industry. So here's just a video. I hope there are also audio.
One in the frame.
Alita is probably the most ambitious digital character that we have created.
That's so good.
There's no better way of doing that than capturing a performance from a real human.
Performance capture gives you the body and the weight and the realism of the expressions.
The way the performance capture process worked is we had a number of cameras placed around the set that would record markers on the actor's physical body. The system would interpret that marker and put it into three-dimensional space and create a skeleton to go inside a CG model to drive that CG model's performance.
This body, it has the power I need. I feel a connection to it. I can't explain. This could be who I am.
Yeah, so you see like the really high quality human motion, what you can get is really from this motion marker-based motion capture system, right? You have lots of cameras around the actor, and you also put markers on the face, markers on the body. That's how you get really good high quality human motion. And what we want to do actually is to capture high quality human motion just from a monocular RGBD camera. For example, you can like this, right? So this video is captured by just a Kinect in an actual environment with a random person performing some human interaction, some motions, right? And you can imagine the application behind such a system if you can really capture the motion, for example, in hospitals, or in like for robot, right? Robot can perceive how human move. And in that situation, we cannot really put lots of cameras there. We cannot put markers on the human body because we really want to capture kind of in the wild scenario of an actual person in an actual environment. And this was a state-of-art result before our work. And you can see, like, actually the motion quality is really much worse than the one you see before, right? Because you can understand, I mean, we can understand why, because now we really try to estimate human motion from all these pixel values. It's RGBD, this lots of pixel values with different, like people could have different appearance, could have occlusions, human-sea interactions. So the motion quality is much, much worse. And then the question is, in our work, is how do we reconstruct natural and smooth high-quality human motion in 3D scene with a monocular camera? How do we really push the quality so that it gets closer to the one we get from the motion capture system, right? And the key idea we have is let's learn motion prior from high-quality motion capture data. So such data set, there exists in the industry as well as in the research research institute. So people have captured hours of hours high-quality human motion, right? These are high-quality human motion. And then let's leverage machine learning algorithms. Let's leverage the data. Let's learn a prior from such data to help us to reconstruct human motion from partial observations, for example, monocular images. And next, I will go a little bit into the details. I want to explain that because it's a very simple idea, and I hope you can follow me. So the first question is, how do we really represent 3D human emotion, right? Assuming we have 100 frames of 3D human bodies, how do we represent it? How do we mathematically represent it so that computer can understand it? So our idea is very simple. We use body markers. So those are fixed locations, 3D point on the surface, on the body surface. For example, this is one marker on the feet. Oh, it's fine. And I guess you get what I mean. And then what we do is we compute the velocity between the same marker in the nearby frames, right? We get this vector, and we compute this for all the markers in the nearby frame. We basically get the velocity of all the markers. And we compute this for all the nearby frames, right? And what we get in the end is actually an image. On this image, this dimension is the velocity of a certain marker, and on this dimension is the velocity of all the markers for a certain frame, right? Now we have an image, and as a computer vision researcher with image, we can do convolutional neural networks, very simple neural networks. That's what we did. So basically, we have lots of such like high-quality motion clips from motion capture data, right? And we basically perform a very simple autoencoder. So what is autoencoder? Like, just mathematically speaking, it's basically you have a data point, and you match this data point to a latent space. So, and then you have a decoder from the latent space back to the original space, right? So it's kind of a mapping. So, and then the whole mapping is represented, it's parameterized. Oh, it doesn't work, it's fine. It's parameterized by the parameters of this neural network, right? So this is a very simple autoencoder. And we train that with first reconstruction loss, very standard. The second one is actually a smoothness term loss. So this smoothness term loss basically makes sure the latent space is high-dimensional latent space, it's smooth, right? And this is trained from many, many high-quality motion capture data. And next, I will show you how we use this latent space to help us to reconstruct motions from just monocular cameras. So again, this is data from mocap, high-quality data, test data. We have never seen during the training. We push this data through our encoder. This is a latent space we get, very smooth, similar to the training ones, right? And this is what the previous state-of-art work, right? You can see the motion is very jittery, and if you push this motion through the encoder we trained, which have only seen the high-quality data, this is the latent space you get, right? And what we can do next is to compute the same loss, penalize the first-order difference in the latent space, and then we get a very smooth latent space. And now with this loss, we compute the gradient, not with respect to the network parameters, but with respect to the input. So basically, by computing this loss, we backpropagate this gradient into the input, and this is what we get. So you can see from the very jittered, like non-smooth motion, now just with a monocular camera, we can get, I mean, it's not really as good as that one, but it actually becomes much better, much smoother, much natural human motion, right? So this is a simple idea behind this work. And I'm going to show you more videos. So this is the input monocular RGBD sequence from Keynotes. This is a previous work, and this is a work from, this is a result from our work. So you can see the motion becomes much smoother and natural. Yeah, but I believe there's still like lots of things can be done in this line of work. Okay, so I will continue with the second one, and for this one I won't go into the technical details. I will just show you some results. So the second one is synthesizing virtual humans. So what, like the motivation why we do this kind of human synthesis work is actually we want to bring realistic virtual human behaviors or realistic human behaviors into the simulations for robotics applications. That's really the goal. So basically we want to synthesize realistic human behaviors, and later such behaviors can be used to train robots, right? To really react and work together with real humans. So, for example, this is one work we did last year, and basically what does this work like? What does it do is basically give a 3D environment and also give a test description, for example, sit on the table, and specify which table it is. And now we have a generative model which can synthesize such human behavior. For example, people sit on a table, right? It's just static pose, but it actually can take the 3D environment as well as like kind of language, not really free language description, but kind of action specification into account, and then generate such like human behavior, right? Okay. And the underlying model is actually the same as ChatGPT, right? Transformer model. It's just much smaller, but it's, again, also a transformer models. And these are all random samples, and this is exciting for us because if we are talking about deep generative models, it's really important, like when we draw from prior distribution, for example, a Gaussian distribution, we really get samples that's convincing. And I think in this case, most of the samples are quite convincing, right? So on this line, I think the language specification is please touch the chair, right? So this person has all kinds of different ways to touch the chair with the back, with the hand, right? Okay. So there are more examples. So basically, this is architectural design. And what we did is basically specify the object to interact and specify the actions we want to interact. And you can see these are all the virtual humans we generate in this architecture design, right? So these are more like stand up on the chair, this type of actions. Okay, so that's actually like a human scene interaction. So we have another work also performed last year is about human-human interaction. It's specifically about grasping. So we basically design a generative model which we can synthesize like natural human grasps. And the key is the object should be unseen, right? So it can generalize to unseen object and also generalize to different location of this object. Again, the underlying model is a deep generative model, and it's a variational autoencoder. Okay, so those are all random sampled on the test object. I mean, it's not perfect. There is no physics, so you still see some interpenetration, but you can see like also some food interpenetration here, but you can see kind of really try to this virtual human really try to grasp object. And these are the motion results. So these are unseen object, and also these are random samples. So not really cherry-picked samples, but random samples, right? And also our model works for different body shapes. Okay. So the last work I want to show you is actually a collaboration with Grandmassive Color Research. So the vision part is basically we design an algorithm that can synthesize virtual humans kind of wandering in a 3D environment, right? By, for example, given goals. So these are the goals. And we designed a deep generative model which can generate like natural human behaviors for all kinds of different body shapes, and they have really a diverse behavior. So you can see the goals. The goal is basically reaching each waypoints, and you can see some people try to reach the waypoint fast, and some people try just wandering in this 3D environment, right? So this is a work, yeah. And this year, we basically extend this work. So the video I just showed you is basically we have a 3D environment. We specify the waypoints in the 3D environment that people, virtual human, like reach each waypoint in a diverse way, right? And in the recent, like in the latest work, what we did is also add human-sea interaction. Right? So here we say the virtual human should first sit on one of these chairs, and then sit on these chairs, and then sit on this sofa, and in different ways, right? Not like a robot, but really like real humans. And this is the result we have so far. So you can see they start with the same location, and will be an interesting thing. So you will see like one of the virtual humans actually kind of wants to sit here. But actually, we didn't specify that. So this guy basically follow all the other person really to so this actually are all in our mind. The virtual human doesn't know that. But this kind of like spontaneous and diverse behavior is what we want, like our model to have, right? Okay. So in the last 2 minutes or 3 minutes, I will present this collaboration. So my very first collaboration with architects, with Fabio and Matthias. So what we did is basically we had this exhibition in the Guggenheim Museum in Bilbao, where we populate or inhabit a 3D architecture, like architecture design. I think Fabio can explain it much better, but I will show you the video, and he will explain the video. Okay.
We've been invited to participate at the exhibition at the Bilbao Guggenheim by the Norman Foster Foundation, and there we decided to revisit the Flight Assembled Architecture exhibition project.
Flight Assembled Architecture was commissioned by the FoC Centre in Orléans in 2012. We decided to produce the installation of a city, an ideal city, an utopian city, that would build upon circularity of movements, of mobility, and circularity of construction. We built a 6-meter tall model and scale 1 to 100 in real time during the exhibition with the help of drones.
We took the chance to revive this utopian project by injecting life into it. Life by virtual avatars that inhabit this virtual utopian project. Now this project we do in collaboration with Professor Tang that has developed artificial humans that have their own behavior and react to the virtual environment around them.
At the Computer Vision Learning Group, we work on computer vision, specializing in perceiving and modeling humans. For the FAA Revisited project, our goal is to populate a large digital environment where virtual humans has different identities, diverse body shapes, move and behave naturally in this environment. So we implement efficient and scalable motion generation models that can generate 200 virtual avatars in real time in this large digital environment.
In the exhibition, the visitors can actually witness all these avatars, and also they can take a look at the first-person perspective of these digital humans perceiving the spaces and the vertical village. This, I think, is very interesting because it points towards a future where architecture can first be tested by being virtually inhabited before it's actually built. This is a completely new reality to the design of architecture. And I think this project was particularly valuable for the different research partners because here computer scientists and architects work very closely together, and the groups learned a lot from the individual methods and how they combine into a future of taking the virtual as a reality in the design of architecture.
Okay, so that's all from my side. This as my student, PhD and postdocs, they are the people who are doing the hard work behind all these things I presented today. And if you are interested in the code, model, or data, you can download from our website. And thank you very much.